Welcome to a visual journey through quadratic forms in linear algebra. A quadratic form is a polynomial where every single term has a degree of exactly 2. Common degree 2 terms are variables squared or multiplied together. It is a function that maps an n-dimensional vector to a single scalar value. In example 1, we highlight the squared and product terms. In example 2, we can see constants, which we call coefficients. Let us visualize what quadratic forms look like. We will plot them in 3D with x and y as our variables and z as the quadratic form. Let us start with z equals x squared. This creates a parabolic cylinder. Now z equals x squared plus y squared. This creates a circular paraboloid, a bowl shape. Next is the saddle shape. Z equals x squared minus y squared. It curves up in one direction and down in the other. Finally, z equals x times y. This is also a saddle, just rotated 45 degrees. Now let us see how to represent quadratic forms using matrices. This is a powerful technique. Let us rename our variables. Instead of x and y, we will call them x1 and x2, and collect them into a vector x. A vector dotted with itself gives us the sum of squares, which is already a quadratic form. To represent any quadratic form, we insert a matrix A in the middle, x transpose AX. Let us see what this matrix A actually does. We will write out the full multiplication step by step. The full product looks like this. Let us multiply it out step by step. First, multiply A times x. Then multiply by x transpose on the left. Multiply and simplify to get our final quadratic form. Now let's look at symmetric matrices. The key insight is that the cross-term coefficient is the sum of the off-diagonal elements. Because only the sum matters, different matrices can result in the same polynomial. We always choose the symmetric matrix where off-diagonals are equal. Let's work through 3 numerical examples to solidify our understanding. Example 1. Convert this quadratic form into matrix form. First, identify the coefficients. A is 2, the cross term is 4, and B is 3. Now split the cross term by 2. This gives us 2 for the off-diagonal positions. Finally, we write the symmetric matrix A. Example 2. Given this symmetric matrix, let's find the quadratic form it represents. The cross-term coefficient is the sum of the off-diagonals, which is -2. So the quadratic form is. Finally, let's evaluate a quadratic form at a specific point. Substitute the values, 2 squared plus 3 times 2 times 1 plus 2 times 1 squared. Simplifying the arithmetic, we get 4 plus 6 plus 2, which equals 12. We can verify this is correct using the matrix method as well. Let us recap everything we have learned about quadratic forms. Remember, quadratic forms use degree 2 terms and symmetric matrices to map vectors to scalars. Visually, they form beautiful bowls and saddles. Thanks for watching. Keep exploring the beautiful geometry of linear algebra.